Right, it's time. Any questions from the homework? Projects or exams? Okay, if no question, let's continue. Dun, 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 dun. We have definite integrals. Okay, we said we have something called Riemann sum. Okay, and we have the area under the curve fx. On AB. They mean the same thing, but now what we want is we want a nice notation to denote both. And we came up with, technically not we, Leibniz came up with this. Okay, that's a beautiful notation. Number one, it's pretty simple. It tells you fx, it tells you the interval AB. Number two, it also takes roughly the same format as a Riemann sum. Okay, you have fx, you have delta x, which is the width of the rectangle. You have the width here, except the width now become almost zero because you let the delta x goes to zero when you have infinitely many rectangles. Number three, you have a sum. That sum becomes this beautiful variation of the letter s, okay, which we call integral sign. So the whole thing here captures everything we want, and we know it means Riemann sum. Sounds good? Okay. Now, what we want to do is we want to talk about the properties of definite integral. Number one, the integral from a to b means the area from a to b. What if the starting and ending point of this function are the same, of this integration? What do you think? You start from 2, you end at 2. What's the area under the curve? It's just one line, right? And line doesn't have area, so this is 0. Okay? There's no area. You only have a point. You only have a line. A line doesn't have area. At least you should have a rectangle. Good. Second, from a to b, fx, dx. Is it the same as from b to a, fx, dx? In other words, does it matter if I switch the starting and ending points and make the reverse order? Does it matter? Well, let's think about it. What is this? It's a Riemann sum. Okay, we have done this last time. Fxi star times delta x, and our delta x is b minus a over n. Good so far? Can I do the same thing for b to a? You actually already see it because everything stayed the same. Except for the BA part, right? What do? You do A minus B. Instead of B minus A, because it's always ending minus the starting. Sounds good? So what's the relation between these two? Are they the same? No, they are exactly opposite to each other. Negative. Okay, that means if you take the integral, the default should be from the left to the right. It always makes sense to say, I want to take the integral from 2 to 4. it kind of feels weird that if you want to take it from 4 to 2, but you can. But once you do that, you're going from right to the left. Okay? Once you do that, you take a negative sign. Just remember you do a negative sign and it's totally fine. Okay? Now you see my thing. I always said like it's going to be the area under the curve. Before we say the area under this one on AB, remember? On the interval. But then we abandon this notation. Why? Because on AB can mean from A to B or B to A. It gives you an impression that is, as long as you have the right interval, which direction really doesn't matter because it's on AB, right? Now we want to be careful. We want to say it's from A to B. Why? Because from B to A is going to be different. But both are on AB. So on AB is not accurate anymore. Okay. Number 3. What does this one equal to? Well, number 1, you have 3 points. You have A, you have B, you have C. Okay, what did you do? You take a function. You're forced to take the area from A to B. Second, you start from where the first one ends. Okay, and then you go all the way from where it ends to C. So what do you think that is going to equal to? That will equal to go from A directly to C. You stop, you don't stop, you do it for 2 steps, or you just do it in 1 step. It doesn't really matter. You still got the same area. Sounds good? That basically means if you want to go from La Crosse to Madison, you can go directly, or you can actually take a detour to Tomah and then go from Tomah to Madison. As long as you're starting for the next part match the ending of the first part, so there's no gap, you can always reach the destination. Okay, that's the property of an integral. Aaron?
Now, would that work if it's a different function or no?
Name any functions. That's not the best I can do, but you see the point, right? It doesn't really matter because you're trying to manipulate just the area, the how to say, the horizontal regions you are trying to mess with. It has nothing to do with the function. Okay, so no matter which function, it works. Maybe you want to think more about this case. What if B is here? Sounds good. If you take a detour, which is pretty stupid, by the way, by going to Madison, you first go to Chicago, which means, dude, you're wasting your time. But the second half will be driving back. Sounds good? Okay, does it make sense? Well, let's try to see this. First, you go from A to B. And you're overestimating the area. Good so far? Then what you do is actually integrate from B to C, which means you actually take the blue area. But notice, you're not going from C to B, you're going from B to C. That means you're taking the negative of the blue area. So what you did is actually go with the red, and then you minus the blue. Does it equal to from A to C? The answer is yes. Okay, so your B doesn't have to even be in the middle. It can be way beyond. It can even be on the left of A. Then you just, okay, in order to drive to Madison, you first drive to Twin City. Okay, again, pretty stupid. But you drive to Twin City, and then you drive from Twin City to Madison. It still works. It's just a waste of time. Sounds good? That's the third property. Okay. Number 4. Integral of a constant dx. What's the integral of 2 from 1 to 3? From 1 to 5. What is it? Number 1, 1 to 5. Number 2, this function, I know it. What's this function? It's just a horizontal line, right? For any function, it's going to be hard, but for horizontal line, what's the area? That's going to be 2 times 4, right? It's a rectangle. So this is a rectangle. You just take the height times the width. For example, for this case, you just take 2 times 5 minus 1 because it's a rectangle. All right. Number 5. F plus G. It's probably going to be hard for me to draw, so let's just draw rectangle cases. If this is F, and this is G, then F plus G will be, this plus that will be even higher, right? It will be first F, and then going from here to here, G. Good so far? Then the area under this curve is just going to be the blue area, the black area, plus the red area. Does it make sense here? Okay, so basically if you have a function, the function is a stack, is F, is G stacked on top of F, you got an even higher function. Good so far? Then if you want to find the area below this curve, it's the same as stacking the two areas together. Okay. Similarly, it works for minus. Wrong. These things start to look like what we had before. We do F plus G, F minus CG, F circle G, F dot G, F divided by G. Okay, we're right on the track. Okay. Second, ABCF x dx equals C AB fx dx. What do you mean by that? Okay, you have a function. Now what you do is you stretch this function, you double it. Good so far? The area under the function you just doubled will be double the size of the area before you double the function. Okay, say it again. If you take a function, you double it, you got a new function. The area under this doubled function is going to be double the size of the area of the function you didn't double. Okay, we got a function, you double it. The area under the doubled function is going to be double the size of the area before you double the function. That's basically what it means. Now I can change double to be triple. Okay, or any number of times you want to double it, or even shrink it. You shrink the size by half, the height by half, you keep the width of each rectangle. Of course, you shrink the whole area by half. Okay, that's what it means. Great. Finally, comparison. If you know fx is bigger or equal than gx on AB, what do you think? Who is going to have a bigger area? Make sense here? The one has the bigger function value, has a bigger height for each rectangle, and if you sum them together, of course you have a bigger area. Okay, notice, when I say bigger, I don't necessarily mean a bigger area, because you can take F to be this, you can take G to be this. If you just look at the area, even though F is above G, the area covered by F is actually smaller than the area covered by G. If you're just talking about size. Good so far? But now you should notice, even though this number is small, it's positive. And even though this number is big, it's negative. So I'm talking about this one is bigger than that, not in terms of like the size of the area. It's more about a number. It's like 1 can be bigger than -3. Even -3 is bigger in terms of size. Okay, so keep in mind, net area is what we're talking about. So if you don't feel comfortable using bigger, you can use above. That would be more like accurate if you think about it. The area of this one will be above the area of this one because one is positive, one is negative. Okay. Finally, if we know the lower bound and upper bound of a function, then what does this one mean? This one tells you this. If you already know there's a number capital M and your function is always below that, okay, that means the area under this curve is going to be smaller than this rectangle formed by M and B minus A. If you already know there is a function which is bigger or equal than a lower bound small m, then the area under this curve is going to be bigger or equal than this blue area because you're above. Okay, so basically you're taking one big rectangle and one small rectangle to squeeze the one in the middle and say, hey, you're right in the middle, smaller than the biggest, bigger than the smallest. Okay, of course that's true. Is it useful? Well, remember this. Okay, we don't know what it is. With the help from here, we still don't know what it is, but at least you know this, right? If you're just talking about 0 pi, still okay? Then at least I know this one is less or equal than 1 times pi minus 0, which is pi, and bigger or equal than 0. So even though I don't know what the area is, at least I know it's less than pi. It's not going to be 8. It's not going to be 10. It's going to be between 0 and 3.14 something. For this example, it may be a little bit stupid to do things like that because later this is easy. We can find it. But later for some complicated functions, for some function which you just give up and say, I couldn't find the integral, but it doesn't stop you from telling what the range is. Okay, roughly it's between 0 and 10,000. And most importantly is, at least you can tell it's finite. As long as it's finite, there's hope. Sounds good? Okay, by the way, there was a really interesting thing. A guy whose name is Kip Thorne. He teaches physics at Caltech. And he actually calculated that if you want to do time traveling, you need energy. You need a huge amount of energy. But once you calculate that thing from general relativity equation from Einstein, you find that energy is finite. Okay, so you don't even know what that energy is, but you know that energy is finite. As long as it's finite, there's hope. Maybe eventually, when we have a big enough machine, we can do time traveling. Okay, but if you calculate that energy, you find infinity, then that's the time you give up hope. And just say, well, no matter what we do, give me another 10,000 years, I won't be able to do it because it's infinity. But that energy is finite if you want to do time traveling. It's just so interesting. You know Wolfram? You use it, right? The guy who invented Wolfram, Stephen Wolfram, he was actually a theoretical physicist. He worked with Richard Feynman before he actually came and started the computational language research and everything. So he recently actually went back to theoretical physics and claimed that he found an ultimate model for explaining all the foundation of fundamental physics. And according to his theory, time does not exist. You know, you don't even have something called time. You don't have something happens before and after. Okay. If you're interested, actually, I should save that. Physics project Wolfram. Ho, ho, ho. I put it in the chat channel so you can Google it and try to see it. And if you need a short introduction, here is a short introduction, which is the second link. Just scroll down and try to look at the beautiful graphs he did. And he claimed you can generate the whole space. Okay, everything we had in our world and our mind through this kind of beautiful graph. Even dimension is graph. All right. Read it after class. It's super cool. And if you want to talk about it, find me after class and we can always talk about it. Yeah, time travel. Since we're here, have you guys read something called All You Zombies? Okay, so try to, if you got a chance to Google that thing, is also interesting. All You Zombies. It's a sci-fi, and it's made by Hollywood. The movie is called Predestination. It can be really fun. That's probably one of the short stories I like about time traveling. It's really interesting to create a paradox through time traveling. Okay. Now let's continue with what we have with integrals. Okay. We kind of already did the discussion. Okay. Can you always integrate the function? Since the integration is just a limit, the question reduced to can the limit be does not exist? And we answer this question. It's possible. Okay. That means we need to ask a question before we do the integration. That is the function integrable? Otherwise, don't bother. Okay. And we kind of answer this question through squeeze theorem. For it to be integrable, you have to make sure that the Riemann upper sum equals to the Riemann lower sum when you take the limit, which is, by the way, very hard to check. Okay. Now, of course, we're asking, is there a shortcut? Or if it's hard to check, has anybody checked it for us to that? Is everything okay? Is polynomial okay? Is sign okay? Is everything function we cared about before okay? Because if that's the case, it's the same with derivatives, right? We don't care about other functions for now. Okay, we just care about the simple ones. The answer is a big yes, and even better. Okay, if f has only finite jump discontinuities, then f is integrable. Maybe. Finite jump. That's the two keywords. Let's talk about it. Well, the first function came to my mind, continuous. As long as it's continuous, I think I can do it. You do the rectangles, everything looks just nice and smooth. You take the lower, you take the upper, right? They're roughly the same because it's continuous. If you take a very small rectangle, the maximum and the minimum will be very close to each other. Okay, so Riemann upper and the lower sum will match. You can even have something like this with sharp corner, which means this is not derivative. The derivative does not exist. It's not differentiable, right? But I don't see a problem of actually finding the area under this curve. Good so far? Cool. If continuous is okay, what about something which is not continuous? Well, what about something like this with a hole? Or maybe 3 holes. Or maybe 20 holes or whatever. Does it affect the area under the curve if you just remove one hole, which means you remove one line from the whole rectangles? Doesn't really matter. Can you see that? You remove a line from the rectangle, the area stays the same. Why? Because the line you just removed has 0 area. So that's fine. What about a jump? Can you do the area under this curve? What do you want to do? You definitely want to do this. And then, do you notice you have a left? You have a right? And you know clearly what you're going to use for height on the left and the right, even though they share different formulas, right? From here, you can see even there is a jump. As long as you cut them by the jump, on the left of the jump, you know what to do. On the right of the jump, you know what to do. And what about in total? You just sum them together, right? What's wrong? What's wrong is what happens at right here. The problem is, it's just one line. I don't care if you have a good behavior, bad behavior, or ridiculous behavior, or you're not there. It doesn't affect my area, right? As long as you're finite, as long as I only have 20 jump discontinuities, that means I need to have 21 different parts, right? If I have 1,000 jumps, I need to have 1,001 different parts. I just sum them together, that's fine, right? But things can go wrong, and we have done this before. When you have infinite many jumps. Now, if you remove a lot of lines, each line barely has an area. But now, if you have infinite many of them, it's possible that once you remove all of them, you remove the majority of them. Good so far? So that's the point of jump and finite. Even if you have a million, a trillion jumps within that interval for a long interval, that's fine, as long as it's finite. Okay. Now think about the Dirichlet function. What we said, this is not doable, remember? It's a rational, irrational thing, the rational, irrational thing. Why is this one wrong? Because this one jump, and this one jumps. I don't know even how to draw it. It just keep jumping. So if you remove all the jumps, basically you remove everything. Okay, so that's why this one does not have finite jump. It's not integrable. Last case. What if you don't have jump, you don't have a hole, you have a vertical asymptote? Okay, is it integrable or not? Depends. Okay, this is called improper integral. Okay. We will leave it for calculus 2. Shit, I cannot spell. Calculus 2. Okay, what happens? I can give you some example. Okay, what's the integral of 1 over x from 0 to 1? Do you see the problem? At the 0, you have a vertical asymptote. So basically, you're trying to draw this. Keep going. And where does this one ends? This one never ends. This one has an open top. That's why it's improper. We need to be careful. Second, what is the integration from 1 to infinity 1 over x dx? That would be this part. Can you see why it's improper? Because this one goes forever. Okay, so these two are special cases. Are they integrable? Really depends on what functions you have. Sometimes it is. Sometimes it's not. And do you see why? It's exactly the 0 times infinity case. What happens here? Very small, almost 0, right? But how many do you have? You have infinite many. So it's hard to say. Good so far? From here, you can see actually these two things can be handled in calculus 2. And probably you need to handle it with limit process. But that is really interesting. That is really, really, really interesting. And I will leave it for you to think about it. You take 1 over x, going from 1 to infinity. That's the thing, right? Now what you do is you take this part, you rotate it with respect to the x-axis. What are you going to have? You're going to have a shape like this. It's like a horn. The beauty about this thing is this horn doesn't have an end. It's infinitely long. Okay, but become skinnier and skinnier and skinnier as you go this way. Good so far? In calculus 2, or actually with all your technology now, you can actually calculate. This one has a finite volume. But this one has an infinite surface area. Which you can prove. I will skip the proof. Okay, that's not the concern here. But if you trust what I say, this is a really interesting horn. Okay. That means if you take beers and try to pour it into the horn, because if you just flip the horn with 90 degrees, you got a cup, right? A cup has a, I don't know, open bottom, or maybe not open bottom, continue forever. So the beers hold. You start to pull beers into it, you only need finite number of beers, actually less than 4 liter beer. You can fill the whole horn up. Sounds good? Meanwhile, because it has infinite area, surface area, so if you go to Home Depot, you want to take this horn and paint it red. You take a lot of red painting, okay? If you just paint the whole horn, you could never do it because that's need infinite many paintings. But if you just pour the paint inside, you fill it within 4 liter. But if you paint the surrounding, it goes forever. Sounds weird? Okay, that's why this is called Gabriel's horn. It was invented by an Italian mathematician before calculus was invented. He doesn't understand what infinity is. He does not understand what infinitesimal is. What is something close to 0 but not 0? He doesn't understand any of that. But through mathematics and geometry, he figured out this. So what's the conclusion? Conclusion is this belongs to the God. And this is Gabriel's horn. Okay? Try to Google it if you are interested. It will be part of the exercise of finding improper integrals. Okay. Sounds good? So from now on, what can you say if some function is integrable or not? Polynomials will be all okay. Polynomials are smooth. No jump, no anything, right? Okay, anything that we had before which is continuous, it will be okay. Okay, e to the x will be okay. Ln x is going to be okay. Sine, tangent, cosine, whatever you have will be okay. As long as the interval you have belongs to the domain. For example, for tangent x, you can do the integration because it's always continuous as long as you stay away from pi over 2 because it's undefined there. Sounds good? 1 over x, feel free to integrate as long as you stay from 0. Stay away from 0 and you're fine. Okay, that's basically the lesson learned here. Good so far? Cool. That's all we need. That's all we need for 5.2. Any question before we move on? All right, 5.3. The fundamental theorem of calculus. This is beautiful. Just look at this title. Okay. It's going to be a very important section. And to show my respect, I need to change my background. Which one? Should be this one. Okay. Remember at the beginning, I had this background. This guy here is Isaac Newton. This guy here is Gottfried Leibniz. These guys are the founding fathers. We got 2 founding fathers, okay, of modern calculus. And finally, in this section, we will be able to talk about what they did. Okay, so this is very, very, very important. The idea is quite simple. I hate Riemann sum. That's the idea. Okay, how do you do this? I need to take the limit. N goes to infinity. Sum I from 1 to n. 3 minus 1 over n, and that is fine. Now x I star cube. I need to pick something. I need to actually sum all of them together. It's going to be a pain in the butt. And this is not even a hard function. Good so far? Then what if I want to do this? What if I want to do this? I have so many other stuff. This one is not even complicated. I really don't want to go with Riemann sum. I want something easier, something quicker to calculate the integrals. Good so far? And this is what we did. You're trying to do this. Okay, that's going to be the area. This is going to be fx. This is going to be A. This is going to be B. Good so far? Now this is what I want to do. I want to fix this. Now what I want to do is I want to take this part and make it x. So this one's changing. Still okay, I fix the left end. I let the right end move. Still okay? So as I move the right end to the right, what will happen to my area? My area is going to increase. Still okay? So let me write it down. As x change, the area change. I'm here, and if I move a little bit, I'm here, and my area changed. Good so far? Now my question is, what is the changing rate of the area? If my x changed by 1, my area may be increased by 5. If my x changed by 2, my area may increase by 40. Good so far? But what's the changing rate? What do you think? Number one, you need to take a very small change of this x. So going from x to x plus h. H is small. Good so far? Second, you want to take the change of the area, which is this. Divided by change of x, which is h. Still okay? That's going to be the changing rate of the area. Okay. Number three, you want to let h goes to 0. Sounds good? All right. So you have a very little tiny thing. You increase your x change this much, your area change this much. Okay. Now if you let h goes to 0, what is the limit of the area divided by the width h? When h goes to 0. The changing rate become the function itself. Can you see that? The changing rate is just this. Right? Right? The area divided by the width is what? Is the height if you have a rectangle. Do you have a rectangle here? No, but more or less. Good so far? But when h goes to 0, then that thing becomes exactly as a rectangle, and rectangle divided by the width is exactly the height. And what's the height? The height is the original function fx. Good so far? Cool. What did we just write down? We wrote down the changing rate. The changing rate is fx. The changing rate of what? Of the area is fx. What do you mean by that? That means the derivative of the area is fx. Good so far? If the derivative of the area is fx, what is the area? We're looking for the areas, right? The area will be the antiderivative of fx. Period. Does that make sense here? Okay, that means what? That means if you want to do this, this is your fx, then probably your area is going to be this. Related somehow. Because it's the antiderivative. Good so far? That means if you want to do the integral of this, that's probably you want to check this. Why? Because this is the antiderivative of this. And we just said the area is related to the antiderivative. Make sense so far? Okay, so from now on, for all the stuff, screw Riemann sum. Okay, I just want to do antiderivative, and the antiderivative is freaking easy. Of course, compared to the Riemann sum, which we really don't want to do the sum. Good so far? So everything we learned before from chapter 2 to chapter 4, now we can use it. As long as we know the area, the integral, the area, they're the same thing, right? The area and the integral is related to the antiderivative. So finding the area, we don't go with Riemann sum, we go with finding the antiderivative. That will be the key. Sounds good? That's genius work. Okay, that's what these two guys did. Of course, that's actually what Leibniz did. Okay, Newton actually did the derivative. That is, the changing rate is going to be the velocity. He was trying to develop something called flow. He was trying to say, hey, if I know the velocity, how do I find the acceleration? If I know the displacement, how do I go with the velocity? You take the derivative. That's what Newton did. Good so far? Leibniz didn't care about all this. Leibniz was trying to say, hey, if I want to sum a lot of things together to find the area, what should I do? And eventually he found that I should do the antiderivative. Then that's how I found the area. Good so far? So you can see Newton did actually area. If you take the derivative, you find the function. Leibniz did, if you take the function, you take the integration, you got the area. They actually did the same thing. The one straightforward, one backwards. Okay, but actually it's the same thing. That's why we couldn't tell who is the inventor of the whole thing. And I will give you a whole story about how they actually fight each other about who invented calculus, because that's. Do you guys know who are the biggest scientists in the history of science? Who deserve the name of like the top 3, top 5? The first one is Aristotle. Okay, no question asked. Socrates, Plato, they're not as good as Aristotle. Aristotle is number 1. Not number 1, the first, okay, top. The second one was Isaac Newton. The third one was Albert Einstein. That's it. So even though the fight was ugly, it's worth fighting for, because that's basically you will be in the top 3 places in the history of humankind, even for today. So they fight really ugly to fight about who invented calculus. Of course, Isaac Newton won for a reason, which I will tell you later. Okay, it's not a too pretty victory. Okay, is the idea clear here? You take the area, you let the right-hand side change, you fix the left-hand side, just change. Then automatically you will ask, as my x change a little bit, how is my area going to change when I take my change of x to be very small, which means I'm trying to find the changing rate. Turns out it will be exactly the function itself. Okay, some other ideas for you to think about. Here is a circle, right? Now, what's going to happen if you just let the radius become bigger? Your area change. Good so far? What's the changing rate of your area? Okay, you know this. Pi r squared, that's the area, right? What's the changing rate? It's pi times 2r, which is 2 pi r. So what is the changing rate of your area? It happened to be just the other circumference you just added when you just keep increasing this, which is 2 pi r. Right? So what's the changing rate when you add a lot? You keep wrapping to make the area bigger. That will be the last layer you just wrapped around. That will be my changing rate. Good so far? Second, what about a sphere? Do you know the volume of a sphere? Four thirds pi r cubed. Good so far? What's the changing rate of your sphere as you increase the radius? That's going to be 4 thirds times pi times 3r squared, which is 4 pi r squared. Does anybody know what this formula is for? That's the surface area. Coincidence? Well, think about a simple thinking experiment. How do you make the sphere bigger? Through increasing the radius. You can take a pen and paint the whole sphere uniformly. As you paint it, it becomes thicker and thicker and thicker, so the volume becomes bigger and bigger and bigger. Good so far? So as I paint the whole sphere, the volume becomes bigger. What's the changing rate of the volume? That's going to be equal to the last layer I just painted, which is the surface area. Does that make sense here? It's beautiful. This idea works. So if you let some area to change from here to here, the area become a little bit bigger. What's the changing rate of the area? Of course, that equals just this layer you just painted, which is fx. So it totally makes sense. Okay, that's all we have for the ideas. Let's go with the detailed proof next time. We need to actually write down all the details to make sure that we did everything correctly, but this is roughly the idea, which makes sense, which Leibniz did 400 years ago. 400 years. Let me see. 1666. That's 350 years ago, roughly. Okay, this is one piece of big human wisdom in history. Okay, we're right on the edge of it, and we will introduce it tomorrow. All right, that's all for today.